Welcome to today's Explainer. We are taking a really fascinating journey right into the architecture of organic chemistry. And look, instead of treating this like some tedious memorization task with endless formulas, we're going to look at it as reading the actual blueprints of the universe. We're going to see exactly how invisible atoms build literally everything in the world around us.
Okay, let's dive into this layout. This syllabus is going to guide us smoothly from the absolute basics to some incredibly cool real-world applications. We'll hit 1, from vital force to labs, 2, carbon's tetravalent architecture, 3, visualizing 3D molecular blueprints, 4, naming millions of compounds, 5, functional groups and reactions, and wrap up with 6, real-world organic chemistry.
Section 1, from vital force to labs. Let's set the stage before scientists truly understood carbon.
Believe it or not, the science of organic chemistry is really only about 200 years old, and its origin story, pretty wild. Around 1815, a Swedish chemist named Berzelius proposed this thing called the vital force theory. Basically, the belief was that organic compounds could only be created by living plants and animals because they possess this mystical vital spark. No spark, no organic chemistry. But then, in 1828, a chemist named Wohler completely accidentally shattered that entire theory. He was just working in his lab and ended up synthesizing urea, which is an organic compound found in living things, simply by heating up a plain old inorganic mineral called ammonium cyanate. This groundbreaking accident absolutely opened the floodgates. Soon after, you had Colby synthesizing acetic acid in 1845 and Berthelot synthesizing methane in 1856.
And this brilliantly illustrates the massive paradigm shift that birthed modern chemistry. We totally moved away from that mystical vital force theory, the idea that you absolutely needed a living organism to make organic compounds, and shifted into modern lab synthesis. Scientists suddenly realized, hey, if we understand the rules of chemistry, we can methodically build the molecules of life ourselves. And we can do it right on a lab bench using reproducible inorganic mineral sources. Section 2. Carbon's tetravalent architecture. Let's zoom into the micro level.
So the real magic of carbon is tetravalence, its fundamental ability to form 4 distinct covalent bonds. But to understand how it does that, we have to talk about hybridization. When carbon bonds, its s and p orbitals literally mix together to form brand new hybrid orbitals. Take an sp hybrid orbital, for example. It's exactly 50% s character and 50% p character. Think of it using a simple paint analogy. If you mix 50% red paint with 50% white paint, you don't get red and you don't get white. You get a bold, completely new color, pink. Just like that paint, an sp hybrid mixes orbitals to create something with entirely unique structural properties.
Okay, so what does that s character actually do? Well, an s orbital is physically closer to the atom's nucleus. So when a hybrid orbital has a greater s character, like the 50% we just talked about in an sp hybrid, compared to just 25% in an sp3 hybrid, those electrons are pulled much closer to the nucleus. This results in shorter, much stronger bonds, and it actually increases the electronegativity of that specific carbon atom. It's a perfect example of how the geometry at the micro level directly dictates the physical properties and shape of the entire compound.
Section 3. Visualizing 3D molecular blueprints. Let's look at how we actually draw these things. Now, what's really interesting about this slide is how scientists translate complex 3D chemical structures onto a flat page. We use different models depending on what we want to study, so let's demystify these with some everyday analogies. First up, the frame model. This one only focuses on the bond patterns, completely ignoring atom size. Think of it like looking at the bare steel scaffolding of a skyscraper under construction. Next is the ball and stick model, which shows both the atoms and the bonds. This is very much like a set of childhood Tinker toys. It's absolutely great for seeing the exact angles. Finally, we have the space-filling model. This emphasizes the true volume and the van der Waals radii of the atoms. Basically, this is like looking at the finished building with all its walls in place.
But, while those 3D models are fantastic for visualizing, chemists need a really fast shorthand to write structures out on the fly. Enter the bond line formula. If you're a beginner, these might just look like random scribbles or zigzags, but they are actually highly simplified, precise structural representations. In these formulas, we hide the carbon and hydrogen atoms entirely, and we draw the carbon-carbon bonds as a continuous zigzag line.
Here are a few quick, actionable study tips if you're just starting out with these zigzags. The rules are actually quite elegant. First, the open terminals at the ends of the line, those are always methyl groups. Every single junction or point represents a carbon atom. Hydrogen is invisible, but we always just assume it's there to satisfy carbon's 4 bonds. And the zigzag shape itself isn't random. It directly reflects the optimal tetrahedral angles in 3D space. Once you get it, it's brilliant shorthand.
Section 4. Naming millions of compounds. So with our blueprints drawn, how on earth do we organize and name all these molecular neighborhoods? There are literally millions of known carbon compounds out there, and we're discovering more every day. Back in the day, we gave them trivial names, like we named formic acid after the Latin word for ants just because it's found in red ants. If we kept doing that for millions of compounds, total chaos. That staggering number is exactly why a strict, universal naming system is absolutely essential.
That universal system is called IUPAC. And honestly, treat this exactly like learning the syntax of a new language. Here is your clear, step-by-step method to name pretty much any structure. Step 1, identify the longest parent carbon chain. Step 2, number that chain, making sure you start from the end closest to a substituent, or branch, so it gets the lowest possible number. Step 3, identify the principal functional group. That becomes your suffix. And finally, step 4, list any branches, like a methyl or an ethyl, as prefixes in alphabetical order.
The shapes you're naming actually dictate real-world use, and we broadly classify them into 2 main types. On one side, you have acyclic and acyclic compounds. These are your open, straight chains or simple non-aromatic rings. On the other side, we have aromatic compounds. These are very special benzenoid ring structures, like benzene. Setting this up now is crucial, because whether a molecule is an open chain or an aromatic ring changes its physical and chemical behavior entirely.
Section 5, functional groups and reactions.
Okay, so we have our structural frame, but what gives a molecule its specific personality? That would be a functional group. It's an atom or a group of atoms attached to the carbon chain that determines the molecule's specific chemical reactivity. Think about it like a city block. The structural frame is the building, but the zoning determines its function. A building zoning decides if it's going to be a hospital or a bakery. Same here. Attach an OH group and your molecule behaves like an alcohol, such as ethanol. Plop a C equals O group in the middle of a chain, and suddenly you have a ketone, like propanol.
And when these molecules finally interact, reactions happen by breaking those covalent bonds. This is a process called cleavage, and it mainly happens in 2 ways. In heterolytic cleavage, the bond breaks unevenly. One atom aggressively takes both electrons, creating charged ions like carbocations. But in homolytic cleavage, the bond breaks evenly. They share. Each atom takes 1 electron, which creates highly reactive neutral species called free radicals. Grasping these basic reaction mechanisms is absolutely key to mastering how organic molecules interact with each other. Section 6, Real-World Organic Chemistry. Let's look at the big picture. So we understand the micro level, but how do scientists actually figure out what a molecule is made of in the lab? Before we can build, we use quantitative analysis to determine the exact mass percentage of the elements. To measure carbon and hydrogen, chemists use a purely genius combustion technique. Let's break down this easy 1, 2, 3 list. Step 1, you burn a known mass of your organic compound with copper oxide. Step 2, the hydrogen in the compound turns into water vapor, which gets absorbed in a tube of calcium chloride. Weigh that tube before and after, and boom, you have the exact weight of your hydrogen. Step 3, the carbon turns into CO2, which is absorbed in a second tube containing potassium hydroxide. The weight difference there gives you your carbon. It's a completely foolproof way to read the building blocks. Now, why does all of this blueprint reading matter to us? Because this is the foundation of literally everything you use, from the DNA in your body to the gas in your car. The specific branching shapes of alkanes directly dictate how modern fuels burn and perform. The presence of those aromatic rings versus straight chains, that defines whether a polymer is going to be a stretchy rubber band or a super strong bulletproof vest. And those functional groups we talked about, they specifically determine how life-saving medicines bind to receptors in our biology. We've gone all the way from the myth of the vital force to Wohler's lab-made urea, right up to mapping the complex 3D polymers that define our modern world. Understanding the architecture of organic chemistry gives us the ultimate power to read the blueprints of the universe and shape our reality. So I'll leave you with this to think about. From tomorrow's ultra-clean fuels to revolutionary new medicines, what will carbon build next? Thanks so much for hanging out and exploring this with me today. Keep learning, and I'll see you in the next explainer.